Okay. Well, thanks for taking the time to come and listen to the talks today. What I'll be covering is pretty much the installation of the containers and how the processes should work, the choice of the geotextiles that you should be considering or when you're making the choice of the containers. So we'll go through the history of geotextile containers in Australia. We'll look at the container details of the standard containers that we have available, the geotextile properties that you need to consider when designing, the filling and placement procedures that need to take place, any repairs that need, how repairs are affected on the structures, the costs. We've looked at the cost of installation because that's one of the key questions that we get asked from people is the cost of these structures. And we've developed some little spreadsheets that we can work through and that the contractors can work and the designers can use for budgeting purposes. And then just a few case studies at the end of the day, just showing some pretty pictures basically. Okay. So from a history point of view, the first containers went in around the early 1980s around Australia. They were predominantly tube structures. But that really highlighted some of the vandalism issues that we've had around the country. And I don't know what it is, but some people love sticking knives in to see what's inside these containers for some reason. It's the strangest thing, but that's just what we see happening. And what that really drove us down the route was to go to smaller individual containers, because when we had these large tubes that were being vandalized, that you lost large sections. The tubes were 25 meters long, 1.2 to 6 meter diameter. When you cut a hole in something like that, you lose a large section of your structure. So the concept was to go down more individual containers so that if somebody stuck a knife into it, that hopefully you get bored by container number 3 and he'd stop sticking his knife into it, and your structure would stay relatively intact. So that's from a practicality point of view. From a design point of view, there hasn't been any until recently, there's been no reliable design methodology that designers could use to design these structures. And it's relied primarily on me saying, trust me, it'll be all right. I've had a look around the country, and while I'm a nice guy, I'm not too sure how reliable I am. So that's why we went down the route of employing WRL to do the wave flume data for us and to do proper design curves for our structures. The important thing to realize here, and I like to start off the presentations with this sort of picture, is that what we're offering you here is just another solution for your coastal erosion problems. We're not offering you the panacea to all your problems that you have out there. What we see is our primary function is back of beach structures where you've got lots of pedestrian access, that you want something that's a safe structure that nobody's going to get injured from. Nobody's going to be up and suing you because they tripped over a rock that was half buried in the surf, or they went body surfing and they smashed into a rock that's been pulled out of your structure. If you start talking about offshore structures that are having wave impact like that, we're out of that game. That's not what we're there for. So when we see product or projects that are not suitable for our projects, we'll tell you that we don't think we're suited to those sort of applications. So just bear that in mind. In terms of the design, there was very little wave flume data on it. When I started in this job back in 2001, the first thing was to try and do a literature search and find out what design information was out there. And there really was very little. Back in the 70s, there was some wave flume data done with small sandbags, and we're talking about sort of 200 kg sandbags. But very small localized work, and it was done in North America. It wasn't really robust, and there was nothing that we could use for the design of our containers. And while we advised people on what we thought was right, it was really from anecdotal evidence of we've had the storm come through here, the wave heights were so high, and our structures survived. And that really wasn't adequate to do any sort of design basis. From there, we've developed 3 standard size containers. A 0.35 cubic meter container, and that's primarily used in riverbank protections, in protected areas and protected environments where the wave climate is not too big. What you see is that They're approximately 500 kgs, and they are, you can either have the standard geotextile or you can go for the vandal deterrent geotextile. And what we've got some samples that we'll hand out to you to show you the two different layers. I'll explain in detail the advantages of the vandal deterrent geotextile a little later. But primarily the 0.35 cubic meter containers, we really wouldn't recommend any of those on open ocean front structures. This is for around boat harbours or riverbank protection. Okay. The next container size was the 0.75 cubic meter containers, and those were used extensively along the east coast of Australia for a number of years. And this primarily was because that was the size of container that could be filled and placed easily, and we didn't have a great deal of knowledge on the stability of these structures. What we're seeing now with experience is that these structures, they can be used on open exposed or in beach environments, but they should be sheltered beach environments. We really be pushing the 2.5 cubic meter containers in these areas. And what you're seeing is that the dry weight around 1,200 kgs for a container like this, and again comes in with a standard geotextile or a vandal deterrent geotextile. The 2.5 cubic meter containers were first developed in 2001 when the Marucci groins were constructed. We'd identified by that stage that the 0.75 cubic meter containers were too small for that sort of application where it was a groin structure going out into the open ocean. And at that stage, Angus Jackson from ICM did some best guesses and some rough calculations and said, well, we need a 2.5 cubic meter container. We as the manufacturers sat down and said, right, what can we manufacture and what sort of equipment can we build to produce a container that size? And that's where the 2.5 cubic meter container came from. So understand that none of these containers that we've developed here are based on any scientific thing other than what's the equipment that we are going to use and how can we place these containers. So it's more from an experience point of view. Like I said previously, you can have any container size that you like. In terms of making these things, there's an infinite number of combinations that you can have. The practical side of it is how do you pick them up, how do you move them, how do you fill them? And that's where we've tried to standardize these structures so that we can do something that's the most cost effective. The other option, the other extreme of this is the mega containers, which are the big tubes. And these range from 20 meters to 50 meters long, circumferences from sort of 4 meter circumference up to 16 meter circumference containers, which are really large items. What you see here down the bottom here is a breakwater down in Port Phillip Bay. These are a stack of 3 containers on top of each other, 40 meter long tubes and a 12 meter circumference tubes being used in there. And then Narrowneck Reef over here. And if you want to ask any questions, Horst here was the skipper on the split hull barge that placed these mega containers. These were 20 meter long containers dropped through the base of a split hull barge into position. Okay, from the geotextile properties point of view, there's a number of factors that we have to take into account when we're designing with these structures. The sand retention, the type of damage that you'd be expecting on site, whether it be incidental damage from driftwood or boats, or vandalism, UV resistance and abrasion resistance. And I'll go into a bit of detail on each one of those areas now. So from a sand retention point of view, it's critical that the geotextile retains the sand within that container. What we've seen from the Umarachi work that James spoke about is, as you have the lower the sand content in the containers, the less stable those containers become. So you don't want a geotextile that allows sand to be washed out from inside of it, because slowly but surely it become less stable. So it's important that you choose the geotextile that'll retain the sand that you're using on the site. Now there are test methods that are available that you can send us your sample of sand that you have on site. We'll test it in conjunction with the geotextile and say, yes, that will retain the sand, or no, it won't retain the sand. And we have to either change the geotextile or we change the fill sand. So it's important that we know what those factors are. The current range of geotextiles that we use, we've tried to develop them such that they deal with the sand that we have on the east coast of Australia at the moment, a very fine silica sand that we have there. And what we're finding is that we retain 99% of this, the sand within that geotextile. But if you've got something unusual, we'll test it for you. In terms of incidental damage, the big area that we have damage from is driftwood. And Neil will show you some photographs of the impacts of Cyclone Yassi up north recently on some of our structures, where large trees have been dragged across the structures and have damaged them. The other ones is boats. Now, we can, just so that you know, we can take boats driving into the containers and actually running up the containers, but they're not resistant to pop cuts. The containers, I have yet to find a geotextile that will deal with pop cuts from a boat. It's virtually impossible. The other key characteristic to realize with these containers is not purely the strength of the geotextile. It's the ability of the geotextile to absorb the forces that when that boat or that driftwood hits into it, that it actually flexes. So while strength is important, elongation at the same time is just as important. So it's much the same as taking your glass there and dropping on a concrete surface. It'll shatter because it doesn't flex. You take a plastic cup the same size, you drop it and it'll bounce because it can flex. And it's the same thing with the geotextiles. What you want is a geotextile that's reasonably strong, but is also flexible to absorb some of those impacts. From a vandalism point of view, this is where it becomes a little tricky. And what we've seen over the years, that this is really the highest risk that we have for any of these exposed structures. That vandalism is something that occurs on every one of our structures that we've done. And it's, like I said earlier, that's pushed us away from the tube structures. And what you see over here is a structure in New Zealand, St. Clair's Beach. And this was a 200-meter long structure, and there were 5 tubes placed on top of each other for 200 meters, and somebody has walked along there with a standing knife and slit every single one of those tubes, the full length of the structure. And it's just, the whole structure's collapsed due to that problem. The product in that one was a woven product, and which is slightly less vandal resistant. Our products, the non-woven staple fiber geotextiles, are also susceptible to vandalism damage. Not as much, but they are still susceptible. The standard materials are far more susceptible. While that figure that you see there, that cut that you see there is quite large, it can still be repaired at the earlier stages. The moment, though, that you have water going over the top of that thing and it started pulling sand out of it, you may as well take that container and throw it out and replace it with a proper container. If you catch it early, you can do repairs on these structures. Okay. Just to give you an example of what this is just a site example. I went up to a job, we had a job up in Cairns, and the council phoned me and said, look, this structure's falling to pieces, it's a disaster, it's not working terribly well. So I flew up to go and visit them, and I thought I'll just go and have a look at the structure before I got there. And there was a bunch of kids sitting on the structure fishing. And this guy was sitting with a knife in either hand, sitting there while he was waiting for the fish to bite, just stabbing holes in the containers as we were talking. So just be aware of that as part of one of the issues with the containers. The fishermen like to stick holes in it so they can put their fishing rods in. These long slits are the issue for the tubes, and you're not going to repair that container, unfortunately. Okay. Because of this issue, we had to come up with a solution to try and minimize the risk of vandalism with these containers. And what was developed was a geotextile that looks pretty much like a peanut butter sandwich. Basically, you've got the base geotextile, which does all the work. That's the strength, where the strength comes from, where that's what the main product is. On the top of it, you've got a very open pore size geotextile. And what that geotextile is there for is it traps sand within that layer. So it effectively traps between 3 and 4.5 kilograms of sand in that outer layer. Now, while that geotextile does provide some strength in it, the main strength is held in that main area. What that does is just protect this geotextile. It protects it from knife cuts. And what we found was that once you get a knife and you try and slit it, because it's trapped so much sand in that, your knife blunts off very quickly. So we did some recent exhumations up at Maroochydore, and I cut the top off a 2.5 cubic meter container. And it took me 7 Stanley knife blades to cut the top of the container off. I did, with a standard container, 1 Stanley knife blade for a standard container. And that gives you a practical sort of feel for it. We also did some testing where we showed in the laboratory where we used a sharpened instrument that by increasing the mass of the geotextile, that base layer, we can get, as we increase the mass, we get better puncture resistance. But it follows pretty much a straight line. As you increase the mass, the puncture resistance improves. Where the big jump comes in is when you add the sand into that layer there. That sand layer is effectively your protection to the geotextile. And what you're getting is a material that naturally accretes in the geotextiles themselves. So this is not something that you're having to add in the factory and add cost to your material. It's just something, when you finish building your structure, we'd recommend that you dump a load of sand on the top of it just to get that sand into the containers. Okay, the next one is UV resistance. And what we've got to bear in mind is geotextiles were developed initially to be buried as filtration medium in subsoil drains and so on. So the whole concept of geotextiles was developed around the concept that you'd bury it within 2 weeks of it being exposed. What we're doing with these geotextiles is a long way away from what the traditional use of geotextiles were. So we've had to rethink the way we've developed the geotextiles in terms of the specifications of the polymers. You have to be very careful with the way you specify your polymers. And when we order polymers, we have to be very careful with the way we order the polymers used for it. Polyester has a natural UV resistance, so polyester is the fibre of choice. If you go with the polypropylene fibre, you have to make sure that it has acceptable levels of UV retardants added to it. And you rely heavily on the manufacture of those polypropylene fibres to ensure that you are getting that. We've had some issues with our yarns that we use, which were polypropylene yarns, and we've just changed that recently, where the suppliers, we believe, have forgot to add UV stabilizers into one batch that they've made. And we've had some failures with the seams because they failed to do it. What that's prompted us to do is change the way we manufacture our containers now so that we don't use the polypropylene yarns in them. We've changed the seam configuration so that those aren't in there. But UV is an issue. And so when you're doing a design, make sure that the suppliers supply you long-term UV results. A simple 500-hour accelerated UV test is what is used for geotextiles that are buried in subsoil drains. We're saying that you should be doing a minimum of 2,000 hours accelerated testing, and if not more. If you can get more, the longer it is, the better it is for you as a designer. Abrasion resistance is the next area that's important, and particularly with these structures that are in the nearshore zone where you've got a lot of sand movement washing up against the containers. What you're seeing is a structure in the nearshore zone, and what you're seeing on the surface of those containers is effectively the fibres fluffing up on the surface of the containers, and that's from particles being dragged over the surface of backwards and forwards over the surface of the container. And if that continues for a long period of time, that will thin the material out and reduce the strength of it. So you have to choose a geotextile that has enhanced abrasion resistance. Now what we have in our laboratory is this piece of equipment here, and that looks like a 45-gallon drum with individual plates, flat plates on it. You bolt the geotextile into that inside plate, and we put in a mixture of sand and gravel, and we rotate it for 80,000 revolutions, and we measure the strength of the geotextile at the beginning and then afterwards to see the strength that the geotextile has. And there is a marked difference between different geotextiles. So when you're designing, request abrasion resistant results for the geotextiles.